The way they work is the third law. When the prop spins, the prop puts a force on the air, and so the air puts a force back on the prop. But if you're in outer space, there's no air. So the only thing that happens is the prop would spin. There is no force on anything. There's no force on the air, so there's no reaction of force to make it go. And so airplanes with props don't work in outer space. In fact, airplanes with props have an upper ceiling. They can only go so high. The air gets thinner and thinner and thinner. And so at some point, they can't work. And it could be from the prop, but it also could be the aerodynamics. The wings need the air, and also could be the oxygen needed in the engines. But there's many reasons why airplanes have a ceiling. But one of them is right here, is this spinning prop. And that's why then, to go to the moon, or to put up a satellite, well, you need something a little bit different. And that's really the difference between a rock and a jet engine or a prop. This rocket, and this is hopefully a good illustration here, is this is my cart, and I'm going to imagine this, or think of this as my rocket fuel. And so the real difference is a rocket carries with it the molecules it's going to push on. It doesn't have them in the air to push on. We don't have this. Whoops. Oh, hang on. I set it down so hard I knocked the batteries out. Okay. When it spins, it doesn't have the chance to push the air. And so a rocket works this way. And so I'll pull this pin out here. And when I do this, you'll see these ball bearings roll down. And I would say then there is a force on the ball bearings that way. And so as they put a force this direction, or I should say there's a force on them this direction, the ball bearings will put an equal and opposite on the cart. And so here's my simple rocket. And sure enough, they go that way, the fuel goes that way, and the rocket goes this way. And so that's my little rocket cart. Well, I think you got the idea of Newton's third law, and I probably should move on, but I have a fun one that I actually teased you on the first day. And being summer school, this is only the third day, but in a regular semester, this would be like the third or fourth week, or third week in. But that's why we built this crazy thing. This is our fun little rocket car, because inside of this tank, we have compressed CO2 gas, carbon dioxide. And there's a lot of it. And this valve opens up, and it comes around and comes out this nozzle right here. But it makes a good educational example of a rocket, because when I open this, there will be a force pushing the carbon dioxide out this way. And so if there's a force on the carbon dioxide this way, then there would be an equal and opposite force on the cart that way. And so, like I said, the first day I kind of teased you with it. I didn't go through the physics of it. I knew we were coming, and this is that first of those demos with them. And since the camera's over here, maybe I'll do this. I'll spin it around, and I'll go across this way. So the CO2 will go this way. And I'm kind of hoping maybe you could even see some of the CO2. The CO2, when it comes out, is kind of a white powdery look. And so unlike this cart here, where it spins and you can't really see the air move, this one you might be able to see. It kind of depends on the how cold it is here in the room, and it's actually kind of warm here. But I'll open this up, and hopefully you'll see the CO2 go this way. You'll definitely hear it. It's really loud, and I think you'll easily pick that up even on the video camera. And there might be these things over here blowing around like crazy. And meanwhile, this will put an equal force that way, and it is quite a bit of force. So it'll be enough for me to even get on right it, if you will. And so I'll put it back here, release the plunger, and say, okay, on the count of three, here I go. 1, 2, 3. Oh, and looks like I knocked something down over here. Oh, I blew the trash can down. So the exhaust, if you will, comes racing out, and it's a huge velocity. And so that's always a fun one to do. And hopefully it comes across as fun on the video camera, but I know this one's probably better in live action. But maybe next semester we'll be around and be able to do this in live action. All right, so those are Newton's 3 laws. So we're almost done with the chapter. But before we wrap it up, and it looks like we've been at our hour and 15, but if you give me just a moment, we'll take our break. There are a couple of loose ends related to Newton's 3 laws that I should cover, and would be nice to get it on the same recording here. And that is the following. The first one here is, what is the difference between mass and weight? A lot of people confuse this. And so it's worth taking a moment and saying, what is mass and what is weight? And I think a lot of the reason they're confused is we like to say mass is an inertia, and an inertia is a resistance to motion. And then a lot of other people, certainly non-scientists, like to think, well, yeah, getting something to move is hard because it's heavy, it weighs a lot. And then they associate these two together, and they are not the same. Let me give you a silly example. Again, if you maybe had a new roommate, and your roommate is moving in, and maybe you live on the 2nd story, they've got all these boxes, you might help them move in. And so you would go down the stairs and grab a box and go up the stairs and into the new apartment. And you're probably getting tired after a while. You're picking up these boxes. You're saying, boy, the weight of these things is making it hard. The weight of this makes it difficult to go up the staircase. And I would say not quite the same as mass. Because what if it's the reverse of this? What if this is a roommate that you don't like anymore? You've roomed with them for a couple of years. They're getting ready to move out. They got these heavy boxes, and they go, can you help me move out? Sure. And you pick up a box, you walk to the edge of the balcony, you let it go, and gravity pulls it right down. And you grab the next box, and you get to the balcony, and you let it go. See, the weight is pulling it down. I would say in that case, the weight is not a resistance. Weight is actually a help. This silly example is a little bit like my friend here. My friend who comes over to push is another force. My friend can either be going in the same direction as me, and then I would call them a help, or my friend could be pulling a force in the opposite direction, and then I would say my friend is a hindrance. But either way, my friend is applying a force. It is not the mass of this that is changing, it is the direction of that force. And so mass and weight are just like that. They're not the same thing. If you say that weight is a hindrance, you're thinking about lifting something up because the force, the weight is down, and you're trying to move it opposite of that force. But if you're trying to move something down, if you really just want to take an object and get it off the balcony, and maybe I shouldn't say it was a relationship gone bad, maybe I should say it's trash. And you pick up that trash, it's really nice to have that force of gravity. You just hold over the trash can, you let it go, and gravity takes it down. And so the weight is actually a force. And a force is not necessarily a hindrance. Now, it could be a hindrance if you're trying to go the opposite direction. Whereas when you look at this equation, acceleration equals to net force over mass. The mass always goes in the denominator. The more the mass, the more it resists, regardless of what direction you push. It is not a vector, it's a scalar. It always is a resistance. You could say the same thing about, say, a satellite or the space shuttle or a rocket from SpaceX. When you go out into deep, deep, deep space, you may say to yourself, well, we're way out in deep space, so it doesn't weigh anything. You're right, it doesn't weigh anything. So does that mean you can stand next to it and then tap it with your finger? And because it doesn't weigh anything, it doesn't have any resistance, and it just goes shooting off at the speed of light because you flicked it with your finger? No, it still has a resistance. It still has the mass. And so the mass has nothing to do with the force of gravity. It has nothing to do with planet Earth. The best way I can describe this is to say this has to do with the amount of the material, the matter. You might even say it's something like how many atoms do you have? And so it's hard to move it just because you have atoms. And so the space shuttle has atoms. Whether the space shuttle is on the surface of the Earth launching up, or whether the space shuttle is way out into deep space, it still has mass. It's still hard to get that space shuttle to go, even if it's out in deep space. Now, it's even harder to get it to go off the surface of the Earth. Because not only does it have mass, but you also have a force called weight pulling it downward. And so this weight is a force, and maybe I should say it is a force due to what we will study soon, gravity. And the real difference then is weight being treated as a force would be part of this numerator, whereas mass, just being part of the physical world that resists regardless of anything else, would go underneath there. And so they really are very, very different. And they go in a different location. And like I said, probably the best way to think about it is to remember weight is another force, which may or may not be a hindrance to you. It's also why we use different units. We then are going to measure mass in kilograms, and we've been doing that and been mentioning that. And since weight is just another force, we will put weight in newtons. And so there's that little subtlety there. Well, you know, there is a couple more things that I could and should say about this chapter, and I think I will. But it's been a while. I think we've been here an hour and a half, and maybe it's just a good time for a break. So if we were in class setting, I know we would all need it. You guys would be kind of tired, and eyes would be watery, and people would want to go get some coffee or something and use the restroom. So even though I didn't quite finish it, and I still think there's some real important things to say before we start chapter 4, let me just cut it here, and then after the break, so in 20 minutes, we'll come back and continue on.